Welcome to The Explainer. Today we're diving into a massive, honestly pretty mind-blowing breakthrough in music AI. We're talking about cracking the code of multi-instrument transcription. Now, if you follow the AI space, you know things are moving at absolute light speed, right? But what we're looking at today, this is that long-awaited leap in how computers actually hear and understand complex music. Let's get right into it.
So here's a crazy question to kick things off. Why is it that an AI can write a brilliant novel, code an entire website, or generate a stunning painting in a matter of seconds, but if you ask that exact same AI to listen to a simple pop song, or heaven forbid a heavy metal track or a full symphony, and just write down the notes, it completely falls apart? It's wild. If you're a musician, you already know the intense, often agonizing struggle of sitting by a speaker, pausing, rewinding, trying to transcribe a dense mix by ear. Well, it turns out that exact same bottleneck that drives us crazy, it's been driving AI researchers crazy for years too.
Just so we're all on the exact same page, the technical term for this is automatic music transcription, or AMT. It's essentially the task of feeding a raw audio recording into a computer and having it spit out a symbolic, readable representation of the notes, typically a MIDI file. And look, AI has actually gotten really good at this if it's just listening to a solo piano. But the second you add a bass guitar, a drum kit, maybe a synthesizer, forget about it. The AI gets completely lost in the noise. A full band is just a totally different beast. Okay, let's dive into this and look at the actual physics of the problem. When multiple instruments play at once, they create a really messy, chaotic sonic spectrum. You've got overlapping frequencies where, say, the bass and the kick drum are just constantly fighting for the same sonic space. You have vastly different timbres, right? A flute sounds fundamentally different from a distorted electric guitar. Throw in complex audio effects like heavy distortion, delay, or reverb, and the math just gets incredibly messy. But the absolute biggest bottleneck of the whole shebang: data. There has been a massive scarcity of real-world music recordings that actually come with perfectly aligned note-for-note annotations to train the AI on.
And that brings us to Section 1, the synthetic data problem, which causes a critical domain shift.
This perfectly highlights what we call the domain shift trap. Basically, because researchers didn't have enough real, messy music mapped perfectly to MIDI, they had to cheat a little. They generated synthetic data. They had computers play MIDI files using digital synthesizers. Now, this synthetic data, it is beautifully clean, isolated, mathematically perfect. But real-world audio, not so much. It's got acoustic bleed, distortion, human imperfection, the works. Training an AI solely on synthetic data is literally like learning to drive in a pristine, perfectly programmed video game and then being dropped right into real-world rush hour traffic. It's a disaster. The skills just do not transfer.
And, the data completely backs this up. Previous state-of-the-art models, like the well-known MT3 baseline, relied heavily on that synthetic training. We're talking about 1,500 hours of it. And sure, while they performed wonderfully in highly controlled synthetic tests, their performance degraded drastically the absolute second they were fed a professional, real-world music mix. Because they were stuck in this synthetic trap, older models were simply too error-prone for everyday musicians or musicologists to actually use in their daily workflow.
So let's meet the hero of our explainer in Section 2. Introducing MuScriptor, a massive new open-weight model built to solve this exact bottleneck.
The real secret to MuScriptor's success isn't just a bunch of clever code. It actually comes down to one staggering number: 170,000. That is the number of real, multi-instrument music recordings this model was trained on. We are talking about over 11,000 hours of perfectly annotated real-world audio. And it covers almost every genre you can possibly imagine, from classical concertos straight through to heavy metal. It's honestly an unprecedented treasure trove of ground truth data.
But what's super fascinating here is that the researchers behind MuScriptor didn't try to, reinvent the wheel with crazy, complex architectural tweaks. Instead, they just used a simple, incredibly effective decoder-only transformer architecture and scaled it massively, all the way up to 1.3 billion parameters. They essentially proved that if you want an AI to truly understand real music, the key isn't necessarily some highly complicated new algorithm. It's immense scale. It's fundamentally rethinking the relationship between synthetic and real-world training data. Let's move to and see how this builds in Section 3, the three-stage training recipe, and how MuScriptor actually learns to hear. The researchers developed this genuinely brilliant three-stage training arc. First up, they pre-train using synthetic data. Second, they fine-tune using that massive data set of real-world tracks we just talked about. And third, they align the model using reinforcement learning.
You can kind of think of it like a student's journey, right? They start by reading textbook theory in a totally controlled environment, then they graduate out into the messy, chaotic reality of the real world, and finally, they receive some highly specialized tutoring to really perfect their craft.
Okay, let's zoom in on step 1. The researchers didn't just throw out synthetic data completely. They realized it's actually still highly valuable for that early pre-training phase. They built this really cool on-the-fly synthesis pipeline that took 1.45 million MIDI files and constantly warped them. They applied random sound fonts, pitch shifting, and even intentional detuning. This basically created an infinite number of audio variations, allowing the AI to build up an incredibly strong, flexible baseline knowledge of musical structure before it ever even heard a real song.
So the crucial point is what happens next. In step 2, the AI gets fine-tuned on those 170,000 real music mixes, forcing it to adapt all that synthetic knowledge to the real world. But step 3? That is the real secret weapon, reinforcement learning, specifically an algorithm called GRPO. They took 300 meticulously human-transcribed tracks and used them to literally reward the AI for getting better. This final post-training stage specifically targets those really annoying AI habits. It severely penalizes the model for missing notes, which we call false negatives, and forces it to drastically improve its timing precision.
Now let's transition over to Section 4, customizing the AI output through instrument conditioning.
This is such a cool feature because it gives control right back to the user. Basically, you can tell the AI beforehand exactly what instruments to listen for. Let's say you have a super dense, messy track, but you only want to learn the bass line. You just tell MuseScripter, hey, focus on the bass. And this doesn't just isolate the instrument. It actually stabilizes the AI's predictions, keeps the transcription remarkably coherent as the song changes segments, and quantifiably boosts the model's overall accuracy scores. It acts almost like an anchor for the AI in the middle of a chaotic mix.
But the big question is, does it actually work? Let's look at Section 5, a new benchmark for transcription, to see exactly how much better it performs.
And this brilliantly illustrates the leap in quality. If we look at the older model, your MT3+, sure, the blue lines represent correct notes, but look at all that red. The red represents false positives, the AI essentially hallucinating notes that simply aren't there. It's a total mess. But if you look at the fully trained MuseScripter model, it's just so clean. Those messy red false positives completely vanish. The model has actually learned to ignore the background noise and perfectly track the target instrument.
Now, when we quantify that visual leap, the numbers are just staggering. To put it in perspective, the standard metric here is the frame F1 score, which essentially measures the precise overlap between the human ground truth and the AI prediction. The previous top-tier baseline, your MT3+, maxed out at about 45.54%, but MuseScripter 1.3b, it jumps to an incredible 73.3%. Let that sink in. We aren't looking at a minor incremental update here. This is a completely new standard for what open-weight transcription models can achieve.
And I have to share this really surprising fact because it proves just how adaptable this model really is. It doesn't just work on your standard pop or rock bands. When they tested it on the Dagstuhl choral set, which is a dataset of complex polyphonic human choral singing, literally one of the most notoriously difficult things for AI to parse, the F1 score jumped from 51.0% to 80.7%. That is huge. It proves that MuseScripter generalizes across wildly different genres. It has truly learned how to map complex human audio to symbolic data, totally regardless of the style.
So, what does this all mean? Which leaves us with this final provocative thought. We are crossing a major threshold here. With open-weight AI models like MuseScripter finally conquering the chaotic, overlapping complexity of real-world polyphonic sound, that massive bottleneck is broken. What does this mean for the future of human transcription and music production? Imagine instantly generating perfect sheet music from a Friday night jam session or isolating perfectly transcribed stems from grainy vintage recordings. The line between raw audio and editable music data is blurring incredibly fast. I highly recommend diving deeper into the MuseScripter release to see it in action for yourself. Thanks for joining me on this explainer, and keep listening.